Hello, geometry students. Today we're going to be going over the Unit 9 workbook. So we're going to be going over everything up to the review on Unit 9. This unit is going to be talking about probabilities primarily. And let's go ahead and get started. So I'm going to share my screen and we're going to talk a little bit about what a probability is. So a probability is of an event, and usually we denote it with like P parentheses and then like the event we're looking for. So if you're flipping a coin for heads or tails, you might put heads here, right? So the way we would think of that is, the way you would read that is, what's the probability of getting heads on a coin flip, right? So the probability of an event, and usually it's P and then parentheses the event, is a numerical value between 0 and 1 that measures the likelihood of an event. So it's basically just the chances of something happening. So for example, on a coin flip, what is the probability or the chance of getting heads on a coin flip? Well, that would be 1/2. So getting heads happens half the time. In other words, it's a 50% or 0.5 probability. Okay, so you may see a probability as a fraction, you may see it as a decimal, or you may see it as a percent, right? You probably think of it like a percent a lot of times, right? 50% chance of getting heads. There's a 50% chance of getting tails, right? Or in other words, it happens half the time. Now, the way we generally calculate a probability is the number of favorable outcomes divided by the total possible outcomes. So here is basically the formula for that. In the case of your coin flip, it makes sense because when on a coin, how many heads are there? Well, there's only one side with heads. And how many total sides are there? Well, there's 2 sides. So that's why it's 1 out of 2. So there's only 1 heads, but there are 2 possibilities, right? There's 2 possible outcomes, heads and tails, but only 1 heads in this case is favorable. So let's take a look at some examples. So let's go to this quick check here. It says a toy manufacturer makes 400 dolls. After inspection, 7 of them have defects. An engineer writes the equation to find the probability of a randomly chosen doll having a defect, if the engineer's equation correct. So he wrote the probability of a defect is 400 over 7. Well, that is wrong. That is wrong because only 7 of them have defects. So it says number of favorable outcomes, but that's basically whatever you're looking for. It doesn't necessarily need to be favorable. Like in this case, a defect on the toy is not favorable, but that's what you're looking for. So it's whatever you're looking for divided by the total. So the probability of finding a defect should be, there's 7 things we're looking for, 7 defects, right? Out of 400 total dolls. Okay, now that's the probability here. So the probability of grabbing the next one that I look at will be defective, will be 7 out of 400. That's that probability. Now I want to emphasize that, or emphasize something about probabilities as well, is probabilities are always between 0 and 1. 0 means that it's not going to happen. It's impossible. Okay, so an example of a probability that's impossible would be like, what's the probability that when I roll a regular 6-sided die, what's the probability of rolling a 10? Well, a 6-sided die only goes 1 through 6, right? 1, 2, 3, 4, 5, or 6. So the probability of getting a 10, well, that's 0 because there's no chance of getting a 10 in that circumstance. Whereas a probability of 1 means it's guaranteed. It's guaranteed. So a probability of 1 might be if I roll a die, what's the probability that I will get some number? Well, that's guaranteed to happen, right? So that one would have a probability of 1. Now, the closer you are to 0 means it's less and less likely. So a probability of like 0.003, for example, is very, very unlikely. A probability that's closer to 1, it means it's more likely. So a probability of 0.9 is likely because that's very close to 1. In the example of this one, probability of defect is 7 out of 400. Well, if you put in your calculator, you can see it as a decimal, 7 divided by 400, and that gives you a probability of 0.0175. So this is a very low probability, right? This is like less than 2% probability. So the probability my next one that I grab will be defective. That's a very low chance that that happens. Okay, I hope that sort of makes sense. The closer you are to 0, the more unlikely the event. The closer you are to 1, the more likely the event. Let's just go ahead and skip page 3. I'll talk about it as we go through. All right. So let's go on to page 4. An auto mechanic is inspecting a lot of 350 cars. So I'm looking at problem 1 here, and finds defects in 23 of them. What is the experimental probability that a randomly selected car will have a defect? So what's the probability of finding a defect in this case? So since we're looking for defects, how many in the experiment had a defect? Well, 23 of them out of the total 350. And that's it. You're done. If you want to write it as a decimal, you can do that. 23 divided by 350. And that gives us 0.066. Okay, roughly. You don't have to write it as a decimal, but it might be helpful when understanding how likely an event is. Usually for me, it's easier to see as a decimal. As a fraction, it's hard to tell how likely that is. I can tell it's not very likely, but here that gives me a better idea. Okay, it's a 6.6% chance, right? Moving the decimal over twice, that's 6.6%. All right. With that being said, see if you can do number 2 on your own. So here you're looking for the probability of finding a 4-leaf clover in this situation. Now, hopefully you guys are familiar with dice because they're going to come up a lot. All right. So dice are, those things that you roll when you're playing Monopoly. And this grid represents all the possible outcomes when rolling 2 dice. So you could roll a 1 and a 1, right? Snake eyes. And your total would be 2 here, right? 1 plus 1, the total is 2. You could roll a 1 and a 2, in which case your total would be 3. You could roll a 3 and a 1, in which case your total would be 4, right? And you could see these are all the possible outcomes. So you could roll 4 and a 3, you could roll a 2 and a 5, you could roll a 6 and a 6. So these are all the possible outcomes. So how many possible outcomes are there when rolling 2 dice? Well, you can see in the grid how many different outcomes are there. This is a 6, looking at this square here. This is a 6 by 6 square. So there's 6 times 6 squares here, right? The area of this square is 6 times 6. So there's 36 total possibilities. So that 36 is going to come up in these problems here, because there's 36 total possibilities when rolling 2 dice. So look at question 3 here. What's the probability of rolling numbers that add up to 7 when rolling 2 standard number cubes? Dice. Okay, use the chart to help you solve the problem. So we're looking for numbers that add up to 7. So we can see, okay, 6 and 1, right? Those add up to 7. So if you roll a 6 on one die and a 1 on the other, that adds up to 7, okay? Let's see if there's any other combinations here. Okay, well, 5 and 2, 4 and 3. Similarly, 3 and 4, 2 and 5, 1 and 6. So these are all the possible ways of rolling a 7, right? So how many ways is that? 1, 2, 3, 4, 5, 6. So there's the probability of rolling a 7. So I write it like this. Probability of getting 7 equals 6 out of, how many are total different possibilities? 36. Now, if it's a fraction like this, whenever you get a probability, I always want to see if I can reduce it. So this, in this case, 6 out of 36, I can reduce that to 1 out of 6, right? Dividing both top and bottom by 6 gives me 1 out of 6 as a reduced fraction. So the probability of rolling a 7 is 1 out of 6. See if you can try number 4 on your own. So what is the probability of rolling numbers that add up to 4? Okay, it's done very similarly. It'll be out of 36, right? See if you can do it. Moving on. Okay. Problem 5. A jar contains 7 red marbles, 15 green marbles, 8 blue marbles, and 10 white marbles. What is the probability that a randomly selected marble is not red? Okay, so we want to know what's the probability of getting not red. Not red. So pretty easily, how many of them are not red, right? So how many marbles are not red? So when we look at our totals, we got 7 red, 15 green, 8 blue, 10 white. So how many of those are not red? So 15, right? The green ones are not red. Plus 8, right? Because the blue ones are not red. Plus 10, because the white ones are also not red. So there's 33 marbles that are not red out of the total. So the total number of marbles. Well, there's 40 marbles in total, right? When I add the 7 plus 15 plus 8 plus 10. So the total number of marbles is 40. So the probability of getting something other than red is 33 out of 40. This is a relatively high probability, right? You are likely to get something that's not red. If you randomly select one marble, right? So imagine a bag and you can't see inside, but you're going to grab one marble and it has all these marbles in it. The probability it's not red is actually pretty high, right? It's pretty likely. If I do 33 out of 40, that gives me 0.825. See how that's closer to 1? So if it's closer to 1, that means it's going to be more likely to happen. With that being said, see if you can do number 6 on your own. Okay, same thing, just different numbers. Once you're done with that, let's move on to 9-2. Okay. So sometimes you're given a chart from a survey, right? So people are asked, oh, what type of ice cream is your favorite, right? So types of ice cream. You got vanilla, chocolate, mint, or strawberry. So this is what people have to choose from. 25 people picked vanilla, 20 picked chocolate, 11 picked mint, 7 picked strawberry, okay? Me personally, I'd pick mint, but whatever. So for this quick check, it says, using example 1, what is the relative frequency of mint ice cream? So basically it's just asking, relative frequency is kind of just what's the probability that someone picked mint. So how many people picked mint? 11 people picked mint out of the total, right? So the relative frequency is just like a probability. It's whatever you're looking for divided by the total, okay? So in our case, that's 25 plus 20 plus 11 plus 7. So the total is 63. So 11 out of 63 picked mint. That's it. Easy. Well, I'll talk about this stuff later, so we could just skip that. So I want you to try number 1 and number 2 on your own. It's just like we did with the ice cream, okay? But this time they just have types of sports instead of types of ice cream, okay? They didn't even bother to change the numbers, all right? So the first one asks about How many people prefer baseball here? How many people prefer football? Okay. And then you would just write those relative frequencies down and you're done. Okay. Just like we did for the ice cream example. Once you're done with that, let's go on and move to page 10. Let's just go ahead and work on one of the examples. Okay, so this question 3 here, it says 3 coins are tossed, one after the other. So you flip a coin, you note the result, then you flip it again, then you note the result, then you flip it again, and you note the result. So you could see all the different options that could happen, right? So you could get heads, then heads, then heads. You could get heads, then tails. You could get heads, then tails, then tails. You could get heads, then tails, then heads. You could get tails, then heads, then heads. You could get tails, then heads, then tails. You could get tails, 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 or you could get tails, tails, heads. So here's all the possible outcomes when flipping 3 coins. Okay, so there's 8 total possible outcomes here. So that's what these mean. So the frequency means that's the number of times it happened. So, I flipped 3 coins and it happened 7 times where you got heads, heads, heads. So that happened 7 times. Heads, heads, tails occurred 11 times, so on, so on. So using the results below, what is the experimental probability of exactly 2 tails will occur in the next 3 tosses? So we're doing the probability of exactly 2 tails. Okay, so 2 tails. Okay. I should probably do a capital T since they're using capital T here. So probability of 2 tails. So we're looking at the probability of getting tails exactly twice. So here I would look at these coin toss results here. So heads, heads, heads. Does that have 2 tails? Well, no. You can see this one has 2 tails, right? See how it says heads, tails, tails? So that's 2 tails. Okay. This one also has 2 tails, right? Tails, heads, tails. And then this one also has 2 tails. Tails, tails, heads. So how many in total got 2 tails? Well, these 8 did. These 5 also got 2 tails. And then these 2 got 2 tails as well. So that's 8 plus 5 plus 2. That's 15 times that happened, right? There was 15 outcomes where they got 2 tails, exactly. Out of the total. So what's the total? You add these all together, right? So 7 plus 11 plus 8 plus 3 plus 9 plus 5 plus 11 plus 2. So there were 56 total trials, and on 15 of those trials, they got 2 tails. So the probability that in this trial they got 2 tails would be 15 out of 56. Now let's work on number 4. 3 coins are tossed, one after the other. Using the results below, what is the experimental probability of exactly 3 heads will occur in the next 3 tosses? Exactly 3 heads? Well, that's only this outcome. Okay. See if you can, so probability of getting 3 heads. Okay. See if you could finish writing that one. Let's move on. Question 5. 50 archers shot 6 arrows each at a target. The frequency of how many times each archer hit the bullseye is listed in the table below. Create a probability distribution for the number of bullseyes each archer hit. So, for example, hitting the bullseye 0 times, so that means they missed every time. Well, 3 archers did that, right? So there were 3 archers that didn't hit the bullseye at all. There were 12 archers that hit the bullseye just once. There were 7 archers that hit the bullseye twice, right? And so on. So there's 50 total archers, right? So if you could add these together, it should equal 50. But they already told us it adds to 50 because they said there's 50 archers. So How many of the archers hit the bullseye 0 times? 3 people did. 3 archers out of 50. So the relative frequency there would be 3 out of 50. Or in other words, the probability of someone hitting 0 was 3 times out of 50. So the number of times it happened over the total. It's always over the total for probabilities. Here, 12. 12 people hit the bullseye once out of 50 total archers. Here, 7 archers hit the bullseye twice out of 50. There were 12 archers that hit the bullseye 3 times, so 12 out of 50. 2 out of the 50. 9 out of the 50. 5 out of the 50. Easy. See if you can do the next one. Okay, moving along. So here's the fundamental counting principle. So you probably already know how to count, right? 1, 2, 3, 4. You may even know how to count by twos, 2, 4, 6, 8. You can count by 5s maybe, 5, 10, 15, 20. Count by 10s, 10, 20, 30, 40, and whatever, right? You might be able to count by lots of different numbers. But the fundamental counting principle allows you to count things much faster. So what I want you to think about is this problem here. So imagine you go to the store, you go to this deli, right? You go to this deli and they have sandwiches for sale, a side item, and a drink. Now, if you're going there for lunch, you get to choose a sandwich, you get to choose a side item, and you get to choose a drink. So how many different combinations can you make, right? How many different lunch combinations could you have? Well, you might think quite a few, and you'd be right? You could have a ham sandwich with chips and a juice. You could have a ham sandwich with chips and tea. You could have a ham sandwich with chips and lemonade. You could have a ham sandwich with potato salad and juice. You could have a ham sandwich with potato salad and tea. You could have a ham sandwich with potato salad and lemonade. You could have a ham sandwich with fruit salad and juice, right? You could see, and I haven't even gotten out of ham sandwich yet, right? Then you'd have all those possibilities for turkey, right? With each of the side items, with each of the drinks. You could have a veggie sandwich, matched with any of the side items, matched with any of the drinks. So how many total different combinations could you make? Well, a lot. So the way you would do it is you would simply look at the number of possibilities here. So in this case, you have 1, 2, 3, 4, 5 different sandwiches. So 5 sandwich possibilities. And then you multiply by the number of side item opportunities. So that would be 4 there, times the number of drink options. So that would be 3 here. So 5 times 4 times 3, that's 60. So there's 60 different lunch combinations that you can make. In other words, the fundamental counting principle basically says that if M occurs in M many ways and event N occurs in N ways, then event M followed by event N can occur in M times N many ways. So the example they give is if you have 6 shirts and you have 3 different pairs of pants, that'll give you 6 times 3, which is 18 possible outfit combinations. All right, I hope that makes sense. So you look at the number of options, multiply, multiply, multiply. That gives you the total number of options you can have, total number of combinations. Okay. All right, with that being said, let's move on. Go down. I want you to try number 1 and 2. Try both of these on page 16. Okay, so I covered out how to do it. Here's another example here if you need it, but see if you can do problems 1 and 2 on page 16. Once you're done with that, let's go back up and we're going to talk about permutations and combinations. Okay, so they give you a formula here. It looks scary. Okay, for permutation, it says NPR equals N factorial, is what you read that as, over N minus R factorial for 0 less than or equal to R is less than or equal to N. Okay, well, that looks confusing, but it's not that bad. And I'll show you how to do it. So, I'm just going to write down here. Actually, I'll write up here above permutation. So, forget about the formula for now. Actually, you can forget about it completely because we're not going to use it. I'm going to teach you how to do it in the way that makes sense to me, and hopefully it makes sense to you too. So, imagine there's 10 people running a race. Okay, so there's 10 people and they're all running, right? Physically running. So imagine it's like a foot race. They're running and they're trying to finish the race as quickly as possible. Now, the first 3 finishers get a medal, right? First place gets a gold medal, second place gets silver, and third place gets a bronze medal. So first place gets gold, second place silver, third place gets bronze. Okay, so how many different ways are there for the race to finish? So I really only care about the the first 3 finishers. Everyone else, 4th place and everyone else, they get nothing. So in the end, they don't really matter. So how many different ways are there for the race to finish? Well, how many at the beginning of the race, so before the race even starts, how many different people could get first place? Well, since there's 10 racers, there are 10 different people who could get first place, right? Now, once first place is established, once someone crosses the finish line and gains first place, how many different people could get second place? Well, 9, right? Because first place was already crossed, right? So now there's only 9 different people who could get second place. And once second place is done, how many different people could get third place? Well, that's 8. So the total number of ways for the race to finish, we use that fundamental counting principle, 8 times 9 times 10, and that gives you 720 different ways that the race can end. So there's 720 different ways the race can end. And that's how you do a permutation. Okay. So one of the key things with permutation is that the order matters, right? Right. In other words, if you're one of these 10 racers, it definitely makes a difference whether you're first place, second place, or third, right? That order does matter, right? You'd much rather get the gold medal than the silver or bronze. So order matters in a permutation. Okay, that's one of the key things is that the order does matter in a permutation. So we didn't have to use this formula. You don't have to learn how to use the formula as long as you understand that. And let's work on a couple of problems right now about it. Okay, so let's actually go down and we're going to work on problems 3 and 4 on page 17. So let's work on problem 3 here on page 17. A college student is choosing 3 classes to take during first, second, and third semester from the 6 elective classes offered in his major. How many different possible ways can the student schedule the 3 classes? So there's 6 there are 6 possible classes to take, and there's first, second, and third semester. So we have 3 spots to fill. Now, how many different options does he have for the first semester? Well, since there are 6 different classes he could take, he has 6 options to take for the first semester. But once he's chosen a class for first semester, he can't choose the same class again, right? So once he's chosen a class to go first semester, he would have only 5 options for the second semester. And once he's chosen first and second semester classes, he would only have 4 options for the third semester. So that's 120, multiplying those out, it's 120 different possible combinations, well, permutations that he could have. Let's work on the next one here, number 4. An environment club is electing a president, vice president, secretary, and treasurer. How many different ways can the officers be chosen from the 8 members? So there's 8 different members. We need to select 4 different positions, right? So there's a president, vice president, secretary, and treasurer. Okay, so we have 4 spots to fill. 4 spots to fill. How many different people could be the president? Well, there's 8 different people who could be the president. Now, once the president is chosen, the next they're going to choose, let's say, is the vice president. So how many different options will there be for vice president? Well, if the president's already picked, then you only have 7 options for the vice president. Then you'll only have 6 options for the secretary. And once these 3 positions are filled, you would only have 5 options to pick for a treasurer. Multiplying those together will tell us how many different permutations there are. In this case, 1,680 different ways that they can choose these positions. And again, ordered matters here, right? Order matters. Being president is different than being vice president, which is also different from secretary or treasurer, right? These positions are all different from each other. So that's what makes this a permutation. Okay. So now we've learned about permutations. Let's now learn about combinations. So combination is when the order of objects that you select does not matter. Okay. So I'm going to give you 2 scenarios. One of these is a permutation. The other is a combination. Remember, in a permutation, order matters. In a combination, order does not matter. So imagine you have, you own a company and you have 20 employees. Okay, you have 20 people working for you. And you decide you're going to give 3 of them a raise. So you're going to give 3, you have 3 people to choose from, you're going to give them a raise. Okay, so here's where the scenarios are different. So in the first scenario, you have your 20 employees and you have 3 that you're going to give a raise to. You're going to give one of them a $3 raise. You're going to give one of them a $2 raise. You're going to give them another one a $1 raise. Okay. Now here's the second scenario. You still have 20 employees and you're still going to give 3 of them a raise, but this time you're going to give all of them a $2 raise. So you're going to give each of them a $2 raise. So you decide you're going to pick your 3 favorite employees. You're going to give each of them a $2 raise. Okay. Which of these is a permutation? Which of these is a combination? In other words, in which of these does order matter? So you might say this one is the permutation, and you'd be correct because here order matters. Being picked for the $3 raise is different than being picked for the $2 raise or the $1 raise. Whereas this one's a combination because Here, if you're chosen as one of the employees to get a raise, well, it didn't matter if you're picked first, second, or third, you get the same raise, right? $2. So in this example, order does not matter. In this example, order does matter. So this is a permutation, this is a combination. Now for combinations, we are going to use this formula, okay? But don't worry, it's not as bad as it looks, and I'll show you how to do it. If I was going to solve for this problem here, how many different ways are there to choose these employees? We would have n factorial. Well, what's n in our case? N is the total number of employees, or the total number you're choosing from. So in our case, that's going to be 20 factorial, okay? Over r is however many you're choosing. So in our case, that's 3 factorial. Over n minus r, well, that's 20 minus 3, and then that gets a factorial. Now, I haven't explained what factorial means, but basically it means that number times all the numbers below it. So for example, 5 factorial means 5 times 4 times 3 times 2 times 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, which I believe is 120. Okay, so 5 factorial is 120. So you can imagine how big 20 factorial is, right? That's 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 17, all the way down to 1, right? So 20 factorial is a very large number. But we can simplify this down, right? So I'm going to erase some of this. Okay, so I can have some room to write. So this would be here, this would be 20 factorial over 3 factorial times 20 minus 3, well, that's 17 factorial. Okay. Now, the 20 factorial, I'm going to write it as 20 times 19 times 18 times, and then I'm just going to write 17 factorial. So you know it continues on past 17, right? 17 all the way through, but I'm going to just stop writing there, and I'll show you why. Because underneath this 3 factorial is 3 times 2 times 1, and then we have a times, and then the 17 factorial is from 17 all the way down to 1, right? But I'll just write 17 factorial. You may notice that this 17 multiplied all the way to 1, and the 17 down here all the way multiplied to 1, those can cancel. Okay. So on top, we just have 20 times 19 times 18, and on bottom, we just have 3 times 2 times 1. So on the top is 6,840. Over, and this is 6. So that gives me 1,140 different combinations. So in that scenario I was talking about, where you have 20 employees and you're going to give 3 of them a $2 raise, in this case, order doesn't matter, combination, that would be 1,140. So that would be, the way you would write that is 20C3, because you have 20 employees and you're choosing 3 of them. So combination 20, choosing 3. Hope that sort of made sense. Hopefully that formula wasn't too bad. Here's another example. So here they have 10C4. It would have 10 factorial on top, 4 factorial times 10 minus 4 factorial on bottom. You could see the 6 factorial cancels on top and on bottom like that, right? and then you just calculate it from there. Now remember to distinguish between a permutation and a combination. In a permutation, order matters. In a combination, order does not matter. All right, so a game with balls numbered 1 through 9 allows you to choose 3 of them. If you have the correct 3 numbers in a row, you win. Pretty sure the in a row part indicates that order matters. So that I would say is a permutation. A box has 20 different potato chips. You choose 5 randomly. Here, I would say this is a combination. It doesn't indicate that, if I pull out chip, if I pull out chip 15 and then 14, that's probably the same as picking out 14 then 15, right? So their order doesn't matter, combination. A sports team of 24 people are choosing 2 people to become captain and co-captain. Here, order matters, right? Captain is different than co-captain. So that's permutation. Order matters. Okay. Here they have another, well, let's not worry about this yet. Let's just go down. So let's go down to page 18. We're going to be working on combinations here. Suppose that you choose 3 books to read from a list of 12 books. How many different combinations of the books are possible? So this time there's 12 options, and I'm choosing 3 of them to read. Right? 12 books, I'm choosing 3 of them to read. So this would be 12 factorial over 3 factorial, 12 minus 3 factorial. So this would be 12 factorial over 3 factorial. 12 minus 3, well, that's 9, times 9 factorial. So I'm going to rewrite the 12 factorial as 12 times 11 times 10 times, and I'm going to stop at 9 factorial, so it'll cancel with this 9 factorial. On the bottom, 3 factorial is 3 times 2 times 1, and then it's times a 9 factorial. I'm just going to put 9 factorial because it's going to cancel with the 9 factorial on top. So here, 1,320 on top. So 12 times 11 times 10, that's 1,320 over 3 times 2 times 1, that's 6. Dividing that out is 220. Okay, so one thing to keep in mind is that these combinations and permutation problems, all of them should come out to whole number answers. You should never get a fraction or a decimal. It should be a whole number every time. With combinations or permutations, always they will come out to a whole number. Because you're just counting the number of ways you can arrange it, right? Suppose that you choose 7 books to read from a list of 10. How many different combinations are there? So in this case, there's 10 books, and I'm choosing 7 of them. So it's a combination, 10C7. So this will be 10 factorial on top over 7 factorial, and then 10 minus 7 factorial. Okay. See if you could finish this one up. Okay, I already set it up for you. See if you can finish it up. Okay. Now on this page, 19, I do not want you to follow this example at all. And the reason why is because they did it completely wrong. Okay. So I'm going to just show you how to do it. And the way I show you will make a lot more sense than what they're doing. And not only that, but it'll also be correct, which this is not. Okay, so you can scribble that out if you want, or just put an X. Okay, don't follow that example. I'm going to show you how to do it correctly. So, page 19. 3 pool balls are randomly chosen from a set numbered 1 to 13. What is the probability that the pool balls chosen are 2, 3, and 8? Now, I want to emphasize that it doesn't matter. Does the order matter here? Well, it does not appear to matter, right? Because they just say, what's the probability of getting these ones, 2, 3, and 8? But it doesn't say in that order, right? So if you get pool ball number 3 first or pool ball number 8 first, that seems to be fine according to this problem, right? As long as you get those 3 pool balls. So let's just figure out. So we want the probability of getting 2, 3, and 8. Okay, so if there are 13 pool balls, right, because they're numbered 1 through 13, and these ones are the ones I want. So what's the probability of me, imagine the pool balls are like in a hat or in a bag, and I'm going to grab one at random. Okay, so what's the probability I get one of the ones that I want? So 2, 3, or 8. So any of those, if I pull out 2, 3, or 8, I'm happy, right? For my first draw. So how many different ones, how many options are there for a good draw? Well, there's 3 that are good, right? 2, 3, or 8. There's 3 different numbers that are good out of 13 pool balls. So let's say the bag of pool balls, I randomly grab one and it's one of the ones I want, right? Let's say it's the 2. I'm like, okay, cool. I got the 2. I put that aside. So I've selected the ball. I put it aside. Now, what's the probability that I select? I'm going to grab another pool ball out of here. So it's probably I select another good one. Well, the 2 I've already pulled it out and put it aside, right? So now there's only 2 pool balls that I want, the 3 or the 8. So there's 2 possible good ones out of 13. Well, not 13 anymore, right? Because you've pulled one of the pool balls out. Now there's only 12 in here, right? Because you pulled one of the pool balls out and set it aside. So now there's only 12 in the bag. So let's say I drew out. So like, okay, let's say I pulled out another one of the good ones, right? Let's say I pulled out the 8, all right? So now only the 3 is inside there in the bag. What's the probability of me getting that 3? Well, it's 1 out of 11, right? Because now there's only 11 pool balls. So that probability will be 3 times 2 times 1. Well, that's 6 out of 13 times 12 times 11, which is 1,716. If you want, you can simplify that. 1 out of 286. And you're done. If you want that as a decimal, you would do 1 divided by 286. And that's the end of the workbook. After this is the review. And let me just stop presenting here. Okay, I hope that all made sense. Hope you're able to get through the unit. And if you need any additional help, you could always email me. My email is ttrigg@ofy.org, which is ttrigg@ofy.org. All right. All that. Take care, and I'll see you guys next time.